¿Qué tal, mis amigos de la ciencia del espacio? Soy Astronáutico y el día de hoy, más que un video de divulgación, les traigo una entrevista. Una entrevista muy especial porque acaba de romperse el récord, al otro lado, el récord de altura para un cohete de agua. El grupo Air Command Water Rocket de Sydney, Australia, acaba de lograr 1620 metros de altura. Así como lo escuchan, más de 1,5 kilómetros de altura. La idea es compartir con la comunidad hispanohablante esta entrevista. Para lo cual, aunque la entrevista se realizó en inglés, me voy a tomar el trabajo de subtitularla toda para poder compartir con las personas de habla española qué fue lo que pasó, cómo lo hicieron, qué es el Command Rockets, cómo se organizaron, cuáles fueron sus motivaciones, la iniciativa, cómo se organizó este proyecto, materiales, cosas de seguridad, todo lo que hubo detrás de romper este récord mundial. Vamos a hablar también de este proyecto. Acompáñenme para una entrevista con George Katz de Air Command Water Rocket desde Sydney, Australia.
Hi, I'm George, and if you want to find out more about how this rocket was built, please visit our YouTube channel. There's lots of construction videos there. Now, there will be a much longer video that will go into the full details of launch day operations. There'll also be new camera angles, including a couple from the booster that you haven't seen yet. And we'll also do a deep dive into the data that came from the 3 flight computers that were on board.
Okay, George, it's time to talk about that huge achievement, that super goal that you did and your team did, because we are talking about a water rocket that reached 1 mile, that reached 1,609 meters.
We just squeezed in over a mile. It was like by 33 feet.
For me, it's a mile.
Yeah. We'll take it.
A mile. But I'm glad that you and me use the decimal system, not the imperial. So we're talking about meters and kilometers. It's more than 1.5 kilometers.
Mm-hmm.
It's 1,603 meters. My God.
It surprised me as well. So what was really interesting with Horizon, we really couldn't simulate it well enough. I ran a whole bunch of different simulations to try and get sort of the best estimate for how well this rocket was going to do. But because we can't simulate with foam, there's no simulators that take foam into effect that was used in the second stage. And the first stage, because it's so complex, it's hard to estimate what the drag coefficient is. I mean, I modeled it in OpenRocket to try and get a best estimate, at least to figure out whether it will be stable. So that was kind of the design process that we used to size the fins for the booster to make sure that the whole thing was stable through most of the flight. But yeah, ultimately, to try and predict our original estimates were somewhere between 4,000 and 4,500 feet. Well, I'm sure that'll be in meters down here, the subtitles. But that was kind of our best estimate, what we thought what the rocket was going to do. When it went so much higher, yeah, that was really surprising. When my son read out, hey, it's gone over 5,000 feet. Because after the rocket landed the second stage, it would beep out its altitude so you can instantly know how high it went. And so when we heard that the first digit was 5,000, we thought, wow, okay. and it looked high just from the ground. It looked like it went really high. So yeah, we were definitely happy with how the rocket, it overperformed what our estimates were.
So I understood that you use water in the first stage and foam in the second?
Yes. Yeah. So again, it was just a little bit of shampoo in the second stage, used 2 liters of water, and it was like a couple of small capfuls of foam of shampoo. So not a significant percent.
Okay, I assume that the use water in the first stage give you more power, more thrust.
That's right.
Okay, and use foam in the second one give you more time of thrust.
More sustained burn. That's right.
Okay.
So the idea of the first stage is to get up to speed as fast as you can to the highest speed possible. And that's when you're supposed to release the second stage. We did, however, when we ran the simulations for when the ideal time to release the second stage, so the booster would have gotten up to like 500 kilometers an hour, and that's when it would have been ideal. But that was only about, I think, 0.6 or 0.7 seconds after launch. And I wanted the rocket to coast a little bit, just so it's staged a little bit higher. But originally I was going to do it maybe after 2 seconds. But the problem is if you do it too late, as the rocket's slowing down, the water in the second stage starts flying up inside of the rocket, exchanging with the air. So if you stage it at that point, all the air escapes before the water does. So it was kind of try and stage it a little bit higher just so it looks better. That was, not going for specifically a particular speed. And so we turned it, the compromise was 1.2 seconds after launch was when we decided to stage the rocket at about 150 meters altitude. And from what we had predicted compared to what the rocket did, that's about when it staged, was at about that 100, I think 140, 150 meters was when it actually staged. So it was kind of this balance between don't stage it too close to the ground, but don't do it too late. Because you're trading speed for altitude gains. You would have gained some altitude before staging, but you're losing that speed at which you release. So that was the. I'm sorry, what was the original question? I go off on tangents.
Don't worry, it's very normal because we are talking about advanced rockets. So it's very normal that we lose in all of the variety of things that happen at the same time. Thank you for saying this thing about what happened with the liquid in the second stage when the thrust is decreased. Because of you, I learned of your videos that this acceleration that happened in the rocket when the water finished, they still is up. But when the water is finished, when all the water is done, they suffer a change in the acceleration, and that's why is guys, all the guys that are listening to us right now, when you try to do this kind of parachute that you think that the cone can fall by gravity or things like that, this thing is not working. So I remember that video when colored water that you did that shows in a, I suppose you put like a tubes. In the reason I put the video, you put like a tube with colored water and show how this thing moves as soon the water is done. So
and we did a second experiment where we had a really long tube, and that was part of the research for this Horizon project, was when it's in a long tube, what happens to that water, how much it moves. And we tried putting in baffles to see how a baffle would stop that water moving. So we thought we might have to put a baffle inside of our second stage, but because the second stage was already built, we really couldn't go back and put the baffle in, because that potentially with that you could delay the staging if you could stop that water from moving up. But because we didn't have that luxury in the existing second stage, we had to adjust the timing. So there wasn't much opportunity for that water to move up. But yeah, we did another a video about where we explored a really long tube partially filled with water and using baffles to stop that water moving up. But yeah, that was part of the research project for Horizon.
What was the idea? You told me at the beginning of this interview that the most important thing is you do this kind of thing for fun. So just one day you get up and say, what about if I do the highest altitude water rocket in my life? Or how this Horizon project start, how this idea born?
So many years ago, we built a very similar style rocket. So we wanted to build a two-stage rocket, and because water rockets tend to be long and thin, the problem is trying to support that second stage on the staging mechanism. So it's got to be something that's fairly light, but because of high accelerations involved, you don't want that second stage snapping. And so we thought, okay, well, let's have the 3 booster segments hold that second stage. And so we built this rocket out of bottles. That's probably 13, 14 years ago now. And the rocket flew great. It staged just the way we were expecting it. We blew up a couple of them. But anyway, but that's kind of where the concept for Horizon originated, was from this design for a two-stage rocket. And I always had it in the back of my mind that one day, you know, if it could be built out of carbon fiber, high-performance materials, that's kind of the design that we would go with. And that kind of inspired the original bottle design. And so the idea for Horizon's been in my head for a long time. Originally, it had a different name and it was called Titan, I think. But yeah, that's kind of been in the back of my mind. And so that's why we kind of progressed as we went through reinforcing. We always wanted to see, okay, let's try and reinforce the bottles with fiberglass, how much more performance we can get, which then led to, you know, reinforcing with carbon fiber, then getting rid of the bottles altogether and just making carbon fiber tubes. Once we learned how to do that, then it was kind of a natural progression. Well, can we now actually realize that original Horizon design now with composite materials because of the huge loads involved? And that was one of the things that really drove a lot of the design was, and the complexity in the design was the huge loads. So, for example, when you're holding down a single bottle rocket, you know, that's just a few kilos of force that you have to hold. With Horizon, you're holding down 700 kilos on the pad. So that's the weight of a Formula One car. That's the force that, and now you're trying to release that with a small servo motor. So how do you transfer that small force from a servo motor to actually release the rocket?
700 kilos.
700 kilos on the pad. So while the rocket's sitting on the pad, and you would have seen this in the video, the very large frame that the whole rocket's on, this steel frame, because at the time of release, that rocket then pushes on that pad with that same force that's pushing 700 kilos into the ground. So we really had to have a really strong launch platform that was able to transfer those loads into the ground, so it wouldn't just fall apart or tip over. So that's kind of, once we progressed from sort of the low pressures to the high pressures, that's why the complexity just exploded, that we weren't expecting how we're going to have to engineer each part of the rocket. We had lots of problems getting the booster segments to seal. So we went through a whole bunch of iterations. We'd get leaks in various ways, so we'd have to figure out what actually caused the leak, and then how we go about fix it, how do we reinforce it. So we went through, I don't know how many iterations of different pressure chambers. And even the final ones that we thought were fixed, and they leaked as well. And so we ended up having to do a fix after they were built, sort of new nozzle extensions. And the other thing is, when dealing with these high pressure rockets, is you're working with very tight tolerances on things, on seals. In the entire launch platform, there were 50 different, over 50 different seal points that we had to have within the launcher, within the rocket. So it was making sure that all of those seals, none of those seals will fail at the almost 70 bars of pressure. So yeah, it was a very different sort of project, and why it took so long. It was, you know, something that would seem fairly simple on a bottle rocket, on a rocket that's made out of bottles, now became a complex exercise in how do you solve that mechanically with the materials that we had on hand. Or so, for example, the staging mechanism, originally that was going to have just a single servo motor that would activate what separates it. Can you give me 1 second? Sorry, Paul, I'll call you back. So, sorry about that.
You was talking about that you use one server in the second stage.
And so one of the club members said, you know, what happens if it doesn't stage? You know, should there be a redundant system for staging? So we thought that's a really good point, because we don't want this rocket coming back down that's pressurized. The second stage is pressurized. It lands and it might launch off the second rocket. And so we ended up modifying that whole staging mechanism. So we had 2 different servos with 2 different electronics, 2 different sets of batteries. So they were independent, that could do the staging. So if one had failed, the other one could also activate it. So that added a whole complexity because of the limited space we had to squeeze this into. And so sort of a lot of the design was also driven by safety factors. Okay, well, what would happen if, let's say the staging mechanism fails and it's coming down under pressure? How do we depressurize it once it's on the ground? You know, you can't approach this thing. It's very dangerous.
Yes.
And so we ended up putting just a small hole in the, instead of a non-return valve, there was a small leak in the staging mechanism, so that it would depressurize the rocket in about 50 seconds. So hopefully it would depressurize it while it was still under parachute. If the booster was still under parachute with the rocket, then it would depressurize by the time it hit the ground, and it would be safe to approach.
Now we can clean up the entire
same for the launcher, you know, backup system. So if all of the electronics failed, battery ran dead, we had manual overrides. We could shut off the air, and we could also remotely depressurize the rocket by pulling a string. We had everything could be done electronically, so we had mechanical controls for pressurizing and depressurizing, but if that failed, you could still override it manually. So yeah, a lot of the design also centered about safety factors. That's why we had 2 parachutes, for example, in the booster. Again, 2 completely independent flight computers controlling 2 separate parachutes. So if only one came out, the rocket should still come back safely.
That fits pretty good too.
Not so many luxuries on the second stage. That's really where you're trying to cut down on weight. So we didn't have a redundant system there, but we did put a GPS tracker on it this time. Because last time when the rocket flew as a single stage, it drifted about 1 kilometer away and took us a while to find it. If we were going to go higher, it could have potentially drifted a lot further under parachute. And so we had a GPS tracker. It turned out the rocket landed 20 meters from our launch, maybe 30 meters from the launch site, so it was easy to find. So we didn't need the GPS tracker, but that was there just in case, so we could locate the rocket afterwards.
and how they
Oh,
can
it's
do
a
that
lot of
little
things.
break.
I really
But anyway,
invite
that's all for this week. Thanks for
everyone that
watching.
is
Thank you for
listening
listening.
right now this
Launching in
interview.
3, 2,
He
1,
say
go!
something really important, that is the word redundancy. Please, if you are involved working in a project, maybe not a Horizon, but it's a project, it's a water rocket that you are working for, I don't know, 2 weeks, 3 weeks, consider that work, consider all these things that George is talking about. Do this kind of redundancy, because no one wants to lose 3, 4 weeks, 2 months of work in 2 seconds.
Mhm.
So it's not require a lot of money. It's not require a lot of equipment. Let me show you. No, you. Let me show you guys this little rocket that is there.
George, and welcome to part 35
My
of
kid,
the series. This
that
week we
was
have a look
made
at
for my
the
kid when he
leaks that we
was
saw back
8,
in episode
I
33
suppose.
with the booster
He
segments.
spent a lot of time
We don't want to
because
have to
he
go
was
rebuilding
8
the whole
years
booster
old.
segments yet
So
again.
when
We've
he
considered a whole
finished that
range of
rocket,
options
I
for
tell
repairing
him,
them.
I don't
As
want
a
to
part
fly
of
this
that
rocket.
process, we
He said,
built
why?
another
Because
booster
you put
chamber that
only
uses
one
exactly the same construction
motor
technique.
on there.
And so we're going to
If
try
you
and
put a
repair
redundant
some of this
system,
first,
yes.
and if that works, then
Why?
we'll apply them
Why,
to the
Daddy?
actual booster segments
Because I
themselves.
don't
So
want
let's
that you
first have a look at
frustrated
what
in
we
your
think
first
the problem
attempt.
is, and then we'll have a look at those
That's
possible
right. So
solutions.
let me show you.
Here's a quick recap of the leaks that we saw in all 3 booster segments when we tested them. As the pressure comes up, we can see that the leaks start.
It's not necessary a lot of money or a lot of different equipment to do this kind of thing. It's just use your creativity. And this is a little one, it's a single chamber, but this is the redundant system.
If we have a closer look, we can see
2
the
motors,
differences between
one is
aluminum
connecting, this
inner
is the
layer
door.
and the inner layer
One
of
of
carbon fiber.
the
Here's a
part of
simplified
the rubber
cross-section
band
of the
pass
Here's
here.
the inner carbon sleeve.
This is one of the
along
end
with
of the
attached
rubber band
aluminium
here.
nozzle. And here is the outer
Sorry.
carbon sleeve along with a fiberglass spacer.
Here,
And finally,
pass
we have
from
the
here,
fiberglass layer
and
that
the
comes
other
out
one
of the aluminium nozzle
passing
that's
that part in
supposed
that
to
part.
seal
If
the
one of the
top.
crank fail,
Now, under
you have the
pressure,
other
we
one.
suspect that what's happening
Doesn't
is
matter
pressure
if just
chambers
one
very
of
good.
these is
ever so
working,
slightly like this,
the
which
parachute
means
is
the
out.
laminate
So
of the
do this kind
aluminium
of
nozzle
things.
that doesn't stretch
I don't
too
know
much
how much is this
creates a
thing.
gap here.
$1
These
motor,
pressures
something like
and
that.
a small leak is
So
significant.
try to do this kind
The
of
leak then
things.
travels between the
I
inner
know there are a
carbon
lot
and
of
the aluminium
people
nozzle to the outside.
that
After
is
long
watching this
discussions on
interview
various
and
options, we
knows
decided
about
to go with the
electronic.
following.
Maybe
Shell
it's
for the
easier
inner
for
carbon
them
sleeve,
to
we
make
can
a
add an
circuit,
O-ring, and
separate
over that we
circuits,
add an aluminium
things like
fiber
that.
sleeve with a nozzle extension.
Because if
The
you
whole thing
want to
then
do
gets
this kind of
fixed
thing,
into place.
if you want
The
to
idea of
share
the
with the
oversleeve is that
community
as the composite
your working
chamber
water
stretches
rocketry,
under pressure, it's pressing
the idea
into
is
the
not
aluminium
show
rather than away
a
from
big
it,
crash.
and
It's
hopefully
part of
stabilize
the
the
thing. It's
system.
part of this
Here
life.
you
It's
can
part
see
of the
that
rocketry.
it's this new
Yep.
extension rather than the
But
nozzle, which is
if
now
you,
redundant.
I
So
prefer
let's go
to
for real.
wait
The first
one
thing we need
more
to do is
week
make
doing
special
the
tape.
redundancy
The outside of the
system,
pressure chamber's
but
nozzle
launch
is a bit
again
lumpy and not
and
quite
use it
Yep.
again.
and we
Yep.
can't
So
fit a 2-meter pressure chamber
in
into
this
it.
moment,
We start
Horizon
off by
is
looking at the
available
instruction guide
to
and
use
take a look
again, or
inside
you
the
need
nozzle
to
keep everything
check
aligned.
everything.
Yeah, so we could fly it again. We are going to publish a video soon, probably next week or so, doing a full flight analysis of what happened during the flight and look at the data. Some of the things that also went wrong on the day that we fixed or worked around. But yeah, Horizon is good to fly again.
And finally, we screw on
I'm not sure when the next flight will be, but yeah, no, that everything survived as needed. One thing I was going to mention with, for example, the parachutes on Horizon, we had a choice whether we would make our own parachutes. That's very common in the water rocket industry. We thought, oh, let's use a couple of big umbrellas. And then I thought about, well, everything's happening a lot faster. So if a parachute deploys at higher speed, are we going to rely on, I'm not a parachute expert, what are my sewing skills like? So we decided that we would go with commercial parachutes. Yes, they're more expensive, but they're designed for the job. They're made of the right materials. You know, these things have been tested at higher deploy speeds. So that was just one of the trade-offs we did. Rather than make a parachute ourselves, let's buy a commercial parachute intended for model rockets. Because, you know, if we were to rip a parachute on the way down and destroy the rocket, and we would have saved a few dollars, you know, that wasn't the sort of option. So for some things, yeah, we decided to sort of buy commercial rather than make it ourselves. It just made more sense.
The next step was to surface coat the chamfer.
How? I don't know if you have some number in your mind. How expensive was that Horizon rocket? Oh, so, you don't know.
I couldn't put a definite number on it because a lot of it's also in the tooling. So creating the tools, the mandrels, the molds, 3D printing molds for stuff. So there's like lots of things that led up to it. And also some of the expenses like the flight computers, parachutes that we bought can be used on other projects. So it's not like that it was just spent specifically on Horizon. Overall, I'm going to say we spent maybe, including the launcher, because the launcher is a part of the whole system, $10,000 to $15,000. Which may seem like a lot, but when you spread it out over a number of years, and some of those costs are offset by sort of the ad revenue that comes in, it's no different to, you know, a high performance RC car or, you know, RC planes. People will spend thousands of dollars on those. With model rockets, people fly high power model rockets. An N or an M motor, you're going to spend a few $1,000s per launch anyway, not counting the rocket. So it's that sort of order of magnitude, which is a lot more expensive than what your typical water rockets are. But yeah, it's kind of built up over the years, so there hasn't been a great expense that we had to, you know, fork out. But yeah, I would put it in that kind of category in terms of materials, but that includes the whole R&D. So making multiple rockets, testing them, building test pressure chambers, pressurizing them to destruction. So all of the costs involved in that, you know, all of the materials, and I'm not counting hours, and I'm not counting any travel expenses to, you know, launch sites and accommodation and petrol, and not counting any of that, just the rocket itself.
Yeah, please tell us something, because you were talking about safety. So how much pressure do you use in Horizon?
So Horizon was launched at 1,000 psi, which is 69 bar.
1,000 psi, guys.
So
a tire in a car is 32 psi.
Yeah, so it's significant pressure. Why 1,000? It just looked like a nice round number. That's the only reason why we chose 1,000, because 1,000 looked nice. We didn't design for higher pressure. That was kind of the goal of everything. Pushing much beyond that, then you're putting a lot more stress on everything else. You have to be even more accurate in manufacturing things, even more accurate tolerances. So that was kind of what we could achieve in our garage, in our workshop. So that's basically, yeah, the reason for that pressure.
Please, some safe recommendation with this thing. You have a lot of experience with little rockets, medium rockets, large rocket. As we can see, you have everything complete. Your eyes, your fingers, everything is in place. So tell us some safety recommendation, because many people still consider water rocket as a toy. And if we're talking about pressure and explosion, this is not a game. This is not a toy.
Yeah, so two things. Stay away from pressurized rockets. I see people handling pressurized rockets. That's a big no-no. A regular water bottle, you know, that'll give you a bruise might give you a laceration. If you reinforce it with fiberglass and that thing hits you, it might break a bone. The carbon fiber at the high pressures, they'll kill you. That's what it comes down to. So everything you have to do, especially when you're dealing with high pressures, safety is like the number one issue. Are you going to be well away from it? How are you going to handle unexpected circumstances? Will you be able to depressurize it remotely? How can you disable that rocket without approaching it? So our whole pressurization system for Horizon was completely remote. So we just had an Ethernet cable, was remotely controlled from, we didn't have any high pressure hoses running to us. That was all done at the pad. And again, like I said, redundant systems to be able to depressurize it. But when you're handling water rockets, they'll stay well away from pressurized containers. When you're doing pressure tests, so you will sometimes do a burst test, make sure you're using water, don't just blow it up with air. That helps to contain shrapnel. It's not as energetic. And you want to wear ear protection when you're doing those tests, or you want to be well away. We had one rocket that we had pressure tested this big rocket. It was all fine. We were doing a separate test at a lower pressure and it exploded. We were maybe within 2 or 3 meters of it. My ears were ringing for 3 or 4 hours afterwards. Okay. It was just so loud. So you can damage your hearing. So make sure that you wear ear and eye protection, obviously, but yeah, ear protection is very important when doing burst tests.
Okay, thank you.
After the test, the booster and repeat it 2 more times for the other segments.
So another important aspect is your pressurization equipment and launch equipment should also be carefully inspected and make sure that you don't blow up a part of your pressurization system. I have seen an injury from a fellow water rocketeer. His hose burst, whipped around and hit him in the face.
Oh,
and he split his lip. The rocket was fine, but it was his pressurization system that failed. So make sure that your pump or whatever that you're using to pressurize your rocket, that all of the hoses can carry those kinds of pressures. Maybe if you're using a garden hose that can't handle the pressure, you want to make sure that you're using properly rated equipment for the launcher.
Thank you for saying that, because many people think about the rocket, reinforce the rocket, be aware about the rocket, and I don't know if somebody is thinking about the platform, the connector, the hose for that example. Normally we are not aware about that the platform hose and everything is under pressure too, and this kind of thing maybe fail, and
everything looks deceptively calm. You don't see the pressure, so the rocket pressurized sitting there, the equipment's pressurized, it looks perfectly safe, but yeah, it's not making a noise, it's not making, giving you any warning signs. So yeah, so you've got to really respect everything.
Okay, we have 7 minutes left. So, George, some words, some motivations, please, to the people that is watching this interview and wants to start in this scene, and maybe they watch your videos and want to do this kind of thing at school or as a hobby in the house. So what is your message to encourage people to do water rocket?
Go out there and build. Just start with don't procrastinate, just go out and build a water rocket. After that first launch, this is what got us hooked. You get a lot of performance even from a single bottle. Once you see that first launch, you go, oh yes, you can see how you can improve things. But share your experiences. Learn from others. share your failures with others as well. I think that's really important so others can learn. But just have fun with it. You know, set yourself challenges. See if you can improve those challenges. One thing is don't chase altitude. That's been one of our big driving forces why we've stayed in the hobby. We've never tried chasing a particular altitude. We've always looked at it as an engineering challenge. Oh, let's do this experiment. Let's do this experiment. The end result that sometimes you would fly to higher altitudes, that was kind of the cherry on top. But for us, it's always been about the engineering challenge. The reason why I say don't chase altitude, because what happens is early on you will get better and better, you will improve, but you'll get to a certain point and then it gets much, much harder to get higher altitude still, and you kind of lose interest because I'm having to expend all of this extra effort and resources just to fly an extra 10 feet to my previous one. So that's why I'm saying is don't necessarily chase altitude, chase different challenges. Maybe you can lift a particular payload, maybe you can run some experiments, maybe let's see what kind of bugs you capture on the way up, or pollen, or, you know, look at the broader picture of water rocketry, not just, you know, how high can we go. That's where you'll keep the interest in the hobby. Maybe come up with a new way of deploying a parachute, a simple way, a cheap way. Set those kind of challenges. Break our record, please. Yeah, that would be my words of advice. Don't chase altitude. Experiment. Try different things. If it fails, learn. Have a careful look at what failed. Improve that and try again. Every crash is an opportunity to build a new rocket.
I need that phrase in a t-shirt with your face.
Even though we've done, you know, hundreds and hundreds and hundreds of launches, we still crash rockets. 1 in 10 of our rockets will still crash. It still happens. It's a part of the sport, part of the hobby. Just accept you're going to lose some rockets. Every rocket you launch, expect to lose it. If you get it back, that's a bonus. So don't be disheartened if your rocket blows up or something fails. That's part of the sport.
George, thank you so much to be with us. Thank you so much for share. As I always, you share your knowledge, your experience. That is gold for us. Please check his YouTube channel, Air Command Rockets, and Water Command Rockets. That is a really good channel with a lot of videos, with a tons of videos, and you can see, as George said, there are different things with single bottle, double bottle, triple, double chamber, a lot of things, a lot of experiment, and the most important thing you can see in his videos, a lot of fun.
Yeah, that's all it is. It's just fun.
Okay.
All right. Well, thank you very much for the opportunity. It's definitely been a lot of fun talking to you after all these years. Let's not make this meeting the last meeting. Let's catch up again soon.
And just to add insult to injury, the high angle of attack caused by weathercocking and the asymmetric thrust made the last booster separate sideways and break off a fin. The Sustainer still powered up to 789 feet and landed safely under parachute. We learned some important lessons from this flight and will make the necessary modifications for the next flight.